Okay, this is chapter 4. We're going to talk about dimensions and tolerances and surfaces. Things you'll need when you're doing processes. So what are dimensions and tolerances? Why do we have... You can't make everything exactly perfect, right? So you got to have some kind of tolerance. And these are the, basically, just like the slide says, factors that determine the performance of the manufactured product are the mechanical or physical properties. So this is what you're going to make, right? And how good you can hold your tolerances usually determine how well the product performs. So dimensions are the linear or angular, in other words, size of the components that's specified on part drawing. If you've never seen a drawing, come see me. I'll give you an example, or look one up. Tolerances is how much can vary from those dimensions. And surfaces, this is the exterior boundary of an object with its surroundings. These are very important. I came from hydraulics, very, very important, because that affected everything, how well the valve performed. ANSI is like it's like the Bible. It's like an organization for all the engineers. And they talk about a dimension as a numerical value. So it's a number expressed in appropriate units. It could be inches, feet, angle, degrees, radians, whatever, of measure, and indicate on a drawing and other documents along with lines, symbols, notes to define the size or geometric, in other words, shape, or both of a part feature. The dimension indicates the part size desired by the designer. So this is where the engineer communicates how big something's going to have to be when they make a part. If it could be made with no errors or variations, so you get these tolerances, and basically if you hold these tolerances, you should be able to make it without any problems. ANSI also has a definition for tolerances. A tolerance is the total amount by which a specified dimension, in other words, how big we want it to be, is permitted to vary. It's the difference between the maximum and minimum limits, and there's different ways of expressing that, but basically this is your the range you have to be in. It occurs in manufacturing process, and everything varies, which are manifest by variations in part sizes. Tolerances tells you how much you can vary and still get away with it. Okay, a bilateral tolerance, this is where they give the ideal 2.500, and then they'll do the plus or minus 0.005, right? That's called a bilateral. Variations permitted in both directions. Now this is a unilateral tolerance. It's just, what you see is a plus 0.010, 2.5 plus 0.010, and no negative. And what the engineer is telling us here is he wants it as close to 2.500 as possible. So you can vary on the big side, but you can't get any smaller. This is another way of doing it. 0.2505 is the max. 0.2 or 2.495 is the minimum. Another way of just saying it. This is called limit dimension. Now surfaces, you got what's called the nominal surface. This is how the contour of the part should be made, and this is with the lines from the engineering drawing. Straight lines, ideal circles, round holes, but you're not going to get it right. They're going to vary quite a bit, or not quite a bit, but vary anyway. The actual part is determined by the manufacturing processes. We've all seen holes that weren't perfectly round, or smooth surfaces that really weren't that smooth. And this is called by variation. So why are they important? Well, they got to look pretty, aesthetic reasons. Surfaces affect safety. We all slipped on the bathtub, right? As these things, as you use these things, friction wear will depend on the surface characteristics. The mechanical and physical properties. We see how sticky spools in hydraulics. If we smooth out the surface, made it less rough, usually went away. And assembly, I mean, we've all tried to stick had a burr or something kept us from sticking a bolt through a hole. And smooth surfaces make better electrical contact. It actually affects the performance of the curve. Twinkle, twinkle, little star equals to IR. So you have less resistance with a smooth surface, what I'm saying. Ohm's law. Well, the technology, what we're concerned with is we want to define what we want on the surface, the characteristics of that surface. So we might specify technology, integrity, no cracks, or something like that. And there's a relationship between the process of manufacturing and the characteristics. How you make it depends on what the technology is, or what the engineer is telling you to make it. This is a metal part, right, magnified, and this looks like a metal part that's had some heat treating. Now you can see the surface texture is kind of rough. So you got the hardened part, and then you got the substrate, which is the soft part of the metal. But that surface texture affects a lot of things, and it's important. And also the thickness of that altered layer. How deep do you want the hardening? They're all important. They all affect how the thing's going to work. So we're worried about surface texture. The topography, in other words, we're worried about the physical properties of the surface, and geometric features, in other words, the shape of the thing. When very magnified, anything but smooth and straight. They look rough. They look wavy. They look like it looks like a piece of the desert or something sometimes. Well, vary from product to product. It also reveals flaws. There's a pattern or direction from the process. You can tell when something's been turned. You can just actually see the little grooves that the tool makes. And how you process it, it has a lot to do with the surface texture. There are some deviations from what's the normal, right? And you can see he's got these cracks. There's a lay direction. That's the direction of the tooling. Crater, which is a little flaw. You might have a little inclusion that gets popped out. You got the waviness. You got the waviness height, and then you got the roughness height. And we can actually measure that. We take looks like a little needle out of an old record player, and we scrape that across. We can measure the waviness and the roughness just by scraping along with that little stylus, and it converts it to electrical current. And by how whatever that current spits out, it'll tell us what the shape of or the texture of that surface is. 4 things we got to worry about on surface texture. One is the roughness, which are those little small little grooves and deviations from the nominal. It's determined by the material and also the processes that we use to make it. Waviness, again, this is where you get the big curves on it. Work deflection, vibrate tooling, similar factors. Roughness is smaller. That's what that superimposed means. It can be wavy without being rough, or it can be rough without being wavy, but the waves are the big ones, right? If you think like on top of a lake, if you get those big rolling waves, we can see little chop marks on the big waves. The big waves would be called the waviness. That little chop is the roughness. Now the third element is lay, and again, they actually have little symbols for these things, right? And it's how you make the process, right? And it looks like it's pretty much self-explanatory. I'll just let you look at this. And while you're looking at it, think about how you might make a surface texture like that. Get that type of lay. Alright, the 4th element is flaws. And just by the name flaws, you know it's not going to be good. But you got cracks, scratches, inclusions, some kind of defect on the surface or in the surface. They affect integrity. These things act as stress concentrators, and what will happen is if you've seen like a chip in a windshield and a crack will develop on that, that's because of the texture. It's the stress will concentrate on that. Same thing will happen in any material, but especially brittle material. Surface roughness is the way engineers will talk about a surface. Finish is usually how the person using it will do it. The lay person will talk about it. They're kind of interchangeable, but technically surface roughness, I'll know what you're talking about as an engineer. You say surface finish, I kind of know what you're talking about. When we take that stylus and run it across the surface, right, we'll get these dimensions. We'll get the vertical deviations, the nominal surface, and we'll be able to tell just how rough it is. So we take a length, that L sub m, and we'll measure it, and then we can come up with a term how rough it really is. And there you go. This is how you do it, right? This is the you actually get some calculus here. It's actually the sum of all the y's divided over the surface area times some x. Basically what they're doing is they're just taking how much it goes up or down over some length of material. computers don't do calculus so well, so what they'll do is they'll just take a bunch of Y readings, divide it by the sample size, and that's how they determine roughness. Now, one of the things you got is, again, we talked about the big waves versus roughness, right? The little chop. You go too far over this surface, you're not only just going to catch the roughness, you're also going to catch the waviness, and we don't want that. So what you try to do is just take a little short sample, and the smaller the sample, the better it is. Usually not easy to do, but as technology is getting better and better and better, very small distances. Now this is a spec. This is how you specify the surface roughness. And I'm not going to go over this too much. It's got the maximum roughness, and it's got the minimum roughness. You got the waviness, the maximum waviness, the cutoff length, how big the sampling size, what kind of symbol you're looking for, you expect to make. This comes from, again, the processing, and how far you can space between the roughness. Again, if you use this and have to measure it, get into quality, you'll get more familiar with this, but you're not going to learn it just by looking at this one slide. Now, integrity. Again, we're talking about little defects in the material. And again, this is where stress will come in and concentrate. If you got a lot of defects and flaws in your material, it's not going to last so long. Think about a cheap tool, right? It's not the best material, a lot of defects in it. It doesn't last so long. Get an expensive tool, it's got a little bit better material in it, lasts forever. This is because of the integrity, right? So what you're doing is you're controlling those defects, you're controlling the characteristics of that material, and you don't want to screw this up during the processes, so you got to be real careful on this. As you work a piece of whatever it is you're working, you're putting energy into this thing, right? And that energy can be stored in like stresses, residual stresses. You can do some work hardening. You can cause cracks. You can knock out inclusions. There's all kinds of things you can do while you're processing this thing: forging, extrusion, and machining. Be careful. All right, be careful with this. It's important that you're aware of it. It just amazes me. It just amazes me how tight the tolerances we can hold nowadays. When we were doing hydraulics, we could hold 50 millionths of an inch. You could have some problems like sand castings or something like that. They need a bigger problem, but generally, if you got machine parts, man, 2/1000ths, 2/10ths, it's not hard. Or 20/10ths, I'm sorry, it's not hard to do. And they're constantly working on getting better surfaces. You know, we can hone, lap, polish. I've got a friend over at Georgia Tech. He, about 15 years ago, he was capable of holding a 1 micron finish, which is very good. It's like glass on turned parts. Again, it's just amazing what they can do nowadays. Of course, the better the finish, the more it costs.